Every race car engine explained. Formula One engines. Modern F1 cars utilize 1.6-liter V6 turbo hybrid power units that produce over 1,000 horsepower. The best part about these engines is that they achieve thermal efficiency approaching 50%, meaning they convert nearly half of their fuel energy into power. The combustion chamber pressures in these engines exceed 300 bar. And to withstand these forces, F1 engines use exotic materials like titanium-aluminium alloys for connecting rods and pistons, and beryllium alloys for valve seats. Engine tolerance specifications are measured in microns. The crankshaft alone costs upwards of $100,000 and requires over 80 hours of precision machining. Teams use preheated fuel to precisely 80 degrees Celsius before injection, optimizing combustion efficiency in ways that would be impossible in street applications. The MGUH in modern F1 engines captures waste energy from exhaust gases that would normally be lost, then converts it to electrical energy, which effectively creates power from heat that most engines simply throw away. This technology alone delivers approximately 160 additional horsepower without burning a single extra drop of fuel. NASCAR V8 engines. NASCAR's 5.8-liter V8 engines might seem outdated with their pushrod valve actuation, which is a design that dates back decades, but there's nothing primitive about these 750-plus horsepower power plants. These engines operate within an extremely narrow window of reliability, with connecting rod bearings typically measuring between 8/10,000ths and 15/10,000ths inches of clearance. Any tighter and the engine seizes, any looser and oil pressure disappears. NASCAR engines utilize flat tappet camshafts rather than the roller cams found in modern production vehicles, which creates more aggressive valve opening profiles. The valve springs must withstand forces of over 1,000 pounds and cycle reliably at 8,000 plus RPM for 500 miles straight, a mechanical feat that would destroy conventional valve springs within minutes. The dry sump oiling system in NASCAR engines uses multiple scavenge pumps to pull oil from the crankcase, keeping it in an external reservoir. This prevents oil starvation during high G cornering and reduces windage losses from the crankshaft hitting oil in the pan, a problem that would cost dozens of horsepower in high RPM operation. Drift car engines. In the world of drift cars, torque is king, and reliability is non-negotiable. While grassroots builds often rely on legendary power plants like Toyota's 2JZ or Chevy's LSV8, pro-level drift engines are optimized for one thing: tire shredding performance at any angle. Throttle response is everything, which is why many teams ditch traditional EFI for individual throttle bodies, each trumpet screaming as the revs climb. Oil starvation is a constant threat as extreme angles mean dry sump systems are mandatory, and some teams even use swinging pickup tubes that pivot with the car's attitude. Unlike drag or circuit engines, drift motors prioritize mid-range punch over peak horsepower. Cams are tuned to deliver 90% of torque between 3,500 and 7,000 RPM, ensuring thick clouds of smoke without constant downshifts. And then there's the soundtrack. The aggressive throttle cuts designed to break traction often sends unburnt fuel into the exhaust, creating the gunfire-like backfires that define the sport. Le Mans endurance engines. Le Mans prototypes represent a different philosophy, balancing outright power with 24-hour reliability. The Toyota GR10 Hybrid's 3.5-liter twin-turbo V6 produces 680 horsepower from its combustion engine plus additional electric power, while achieving fuel economy that would have been unthinkable a decade ago. Endurance engines utilize Nicosil-lined cylinders, which is a nickel silicon carbide coating just 0.07 millimeters thick that reduces friction dramatically. This coating is applied through an electrical deposition process that costs thousands per engine, but saves crucial power over a 24-hour race. Porsche's endurance engines employ variable length intake runners that physically change length to optimize torque across different RPM ranges. Their direct injection systems operate at over 200 bar pressure, atomizing fuel to microscopic droplets that burn more completely than conventional injection systems. Thermal management becomes critical in endurance racing. Engineers implement separate cooling circuits for the engine block, heads, and transmission oil, precisely controlling temperatures in each zone. Some systems can vary coolant flow rates to different engine areas based on thermal load, preventing local hotspots that could cause failure. Kart racing engines. Don't let their size fool you. A 125 cubic centimeter shifter kart engine is one of the most intense power plants in motorsport. Revving to a 15,000 RPM, these tiny screamers can out-accelerate a Porsche 911 off the line, thanks to their brutal power-to-weight ratio. Unlike most race engines, karts often forego traditional transmissions, relying instead on centrifugal clutches or direct-drive gearboxes that keep the engine locked in its power band. Induction is where things get interesting. High-end kart engines use rotary valve systems. which is a spinning disc that times intake pulses for throttle response so sharp it puts street bike engines to shame. Durability is another surprise. Weighing under 40 pounds, these engines endure 10+ hours of full throttle abuse between rebuilds, thanks to forged aluminum pistons that seal via taper rather than rings. And then there's the sound, that unmistakable angry bee sound that comes from ultra-short intake runners and open exhausts, tuned not for back pressure but for acoustic wave efficiency. Top fuel dragster engines. Top fuel dragsters represent internal combustion pushed to absolute extremes. Their 8.2-liter supercharged V8 engines produce over 11,000 horsepower. These engines consume nitromethane fuel at over 1.5 gallons per second. The fuel flow is so intense that if you hook the fuel system to a garden hose, it would empty a standard swimming pool in under 30 minutes. The supercharger alone requires over 900 horsepower just to turn it. This is more than many sports cars produce in total. It forces air into the engine at 65 pounds per square inch, compared to 15 to 22 pounds per square inch in most production turbocharged cars. After each run, crews must replace the spark plugs, piston rings, clutch plates, and often the entire clutch assembly. The connecting rods stretch permanently during a run, requiring replacement after 2 to 3 passes. Top fuel engines are essentially consumable items, with rebuild costs exceeding $7,000 per run. The exhaust gas temperature reaches 1,800 degrees Fahrenheit, which is hot enough to melt aluminium, and this explains why the exhaust headers glow bright orange-red during night races. Without the cooling effect of fresh fuel injection, these engines would self-destruct within seconds. WRC Rally engines. World Rally Championship engines face uniquely brutal conditions. Their 1.6-liter turbocharged 4 cylinders produce approximately 380 horsepower, while enduring temperature extremes from Arctic snow to desert heat, often in the same rally weekend. Rally engines employ sophisticated anti-lag systems that keep the turbocharger spinning between gear shifts by injecting fuel directly into the exhaust manifold, creating small explosions that maintain boost pressure. This produces the distinctive gunshot-like backfires that rally cars are known for. The oil pan design is a marvel of engineering, using complex baffling systems and multiple pickup points to maintain oil pressure during jumps, where the car can experience both positive and negative G-forces in rapid succession. Without these systems, the engine would starve of oil and seize within seconds. Rally engines must deliver immediate throttle response from idle to redline, requiring precisely mapped electronic throttle systems and lightweight rotating assemblies. The turbocharger's compressor wheel spins at over 200,000 RPM, which is more than 3 times per second, and must respond instantly to driver inputs. IndyCar engines. IndyCar standardized on 2.2-liter twin-turbo V6 engines from Honda and Chevrolet, producing approximately 700 horsepower. Unlike F1's open development, IndyCar maintains tighter control over engine specifications to keep costs manageable and competition close. Despite these restrictions, IndyCar engines are engineering marvels, capable of sustained operation above 12,000 RPM while delivering exceptional throttle response. Their fuel delivery systems must adapt to both oval tracks where they run at full throttle for long periods, road courses, and where constant acceleration and deceleration demand precise fueling. Engineers focus intensely on camshaft profiles and valve timing to extract maximum performance within series restrictions. The wastegates on the turbochargers are electronically controlled to manage boost pressure throughout the RPM range, preventing the turbo lag that would be catastrophic in wheel-to-wheel racing. These engines must also accommodate multiple fuel mixtures, as drivers can adjust fuel enrichment on the fly for either maximum power or improved economy, depending on race strategy. The mapping to support these fuel modes represents thousands of hours of dyno testing and optimization. Grand Touring and Touring car engines. GT racing categories use engines that begin life as production units before being modified for competition. These engines bridge the gap between what you can buy and what races on professional circuits. Production-based engines in GT3 cars typically produce between 500 to 600 horsepower, achieved through careful optimization rather than exotic materials. Engineers focus on airflow improvements, with intake and exhaust systems designed to minimize restriction while staying within class regulations. The cooling systems for these engines are significantly upgraded from their street counterparts, handling the increased thermal load of sustained high RPM operation. Additional oil coolers, transmission coolers, and differential coolers manage heat that would quickly overwhelm stock systems. While maintaining the production block and head architecture, race teams install forged internals, higher compression pistons, and more aggressive camshafts to extract additional power. The electronic control units feature custom mapping developed specifically for the fuel quality and operating conditions of racing. Next-generation race engines. Formula E's electric motors deliver instant torque without shifting gears. Their power density exceeds 5 kilowatts per kilogram, which is 5 times better than production electric motors a decade ago. The power electronics operate at over 800 volts, reducing current and heat while maximizing efficiency. Hydrogen combustion engines, like those being developed for Le Mans, burn hydrogen in conventional internal combustion engines rather than using fuel cells. This approach maintains the visceral experience of traditional motorsport while potentially achieving carbon neutrality. Toyota's experimental hydrogen engine produces comparable power to gasoline units, but emits only water vapor. Synthetic fuels represent another frontier, with companies like Porsche investing heavily in e-fuels that capture carbon during production and release it during combustion, creating a closed carbon cycle. These fuels can be used in existing engines with minimal modifications, potentially extending the life of internal combustion technology. Race engines push what engines can do, from F1's tech wonders to drag racing's pure power monsters. Each type shows human skill and the quest to go faster, all within the rules of their sport. Which one fires you up? Drop it in the comments. Hit subscribe for more awesome car videos, and don't miss our last video on engine sounds. It's a must-watch for gearheads.